So what we are going to do in this lecture is to continue with the problem that we started in the last lecture. Okay. So by the end of this lecture, there are two things that you will be able to do. One is basically determine the location along the axis of a shaft or a beam where you have the maximum resulting bending moment. That is very critical to find out what is the maximum tensile or compressive stress in the entire shaft. The second thing that we will do in this class is to figure out the points or the locations in the cross-section where the maximum tensile, compressive, and shear stresses occur. Okay? So just to go back to the last lecture, we had this problem where we had a shaft that was loaded by two pulleys, and we essentially found out what are the bending moments mz and my as a function of x. Okay, so we found out individually what mz and my, how the mz and my change as a function of x, which is the axis of the shaft here. What we are going to do in this lecture is to figure out where along the axis of the shaft we have the maximum resulting bending moment. Okay, so and that is what we are going to do in this class. Okay, so how do you go about finding where the resulting bending moment mr is maximum? So typically, if you want to do this for a general case, what you would end up doing is that you write the expression for mr for all the segments along the shaft. So in this case, you have three segments, AB, BC, and CD. And the reason that we have three segments is because in the segment AC, MZ is constant, but MY is not constant. But in the segment CD, both MZ and MY are changing. Okay? So essentially what we have to do is we have to split the shaft into as many segments as there are changes in MY and MZ. Okay? So what we're going to do is we have to first write expressions for MY and MZ as a function of x for each of these segments. Then we have to calculate mr for each of the segments, and then maximize mr for each of the segments, and then pick out the maximum value of mr among all three segments. Okay? So to make it a little bit more clear, so if you look at this particular bending moment diagram, mz and my as a function of x, what we see is that if you look at the mz diagram here, then you look at segment AB, you have mz is equal to 200x. So that is just this straight line over here. And that extends all the way till point C. So mz is 200x both in AB as well as in BC. Okay, so that is the function for mz for segments AB and BC. However, when you go to segment CD, the function for mz is changing. So it goes from 200x from A to C to actually 12,000 minus 400x from C to D. Okay, so those are essentially the functions for mz. Similarly, you can find the functions for my for the segments AB, BC, and CD. So if you look at my, for the first segment AB, it is actually 800x. From the point B onwards, it actually has a downward slope. So which means that it is going to have a negative constant in terms of x. Okay, so you essentially have my to be 12,000 minus 400x. And that is the same straight line that goes all the way from B to point D, which means that the same function is true for the segment C to D as well. So essentially, in this case, what we have done is we have written out the functions for mz and my for segments AB, BC, and CD. Okay? Once you do that, we can find out what mr is. So if you recall, mr is actually square root of my square plus mz square. Okay? So if you think about segment AB, then your mr is going to be fairly simple. Mr of x is going to be square root of 800 square, okay, plus, sorry, 800, let me make this correction here. It is not 800 square, it is 800x, the whole square, plus 200x, the whole square. And if you take out the x, it's going to be nothing but square root of 800 square plus 200 square times x. Okay, so that is the function MR for the segment AB. Okay, now you can also write this for another segment, say let's say segment BC. So here MR is going to be a little bit different because MY in this case is 12,000 minus 400x. So that is going to be square root of 12,000 minus 400x the whole square plus 200x the whole square. Okay. So now what we have done is we have written out the expression for MR for segments AB and BC, and of course you can do this also for segment CD. Now once you have this MR of x, what we can do is we can find out max MR for each of the segments by essentially taking the derivative, or in this case it's just a single variable, so it's dMR of x by dx, and then equating it to 0. Okay, and then you find out what is the value of x for which this function actually becomes 0, and then you ensure that you take the second derivative of MR with respect to x and make sure that the second derivative is less than 0. Okay, so that's the way you maximize MR of x. So what you do is you find MR of x for the maximum MR in each of the segments A, B, B, C, and CD, and you pick the highest value of MR among all these three segments, and that is going to be the maximum MR for the entire shaft. So this is the typical way of finding MR maximum for a general case. So in this case, it doesn't matter what the function is. In this case, all the functions are linear. But if you have a quadratic function or a cubic function of mz or my, you can still use this particular procedure to find out what MR max is. Okay? But when all the segments have a linear dependence, when the bending moment has only a linear dependence of x in all the segments, you have a slightly easier way to find MR or MR max. And that is what we are going to talk about next. So in this case, if you look at this particular problem, you have a linear segment for mz from A to C and also another linear segment from C to D. The same is true for my as well. So essentially you have a linear segment from A to B and another linear segment from B to D. Okay. So when you have a case where the bending moment diagram is completely linear, okay, what I mean by that is both my and mz should have only linear segments. In that case, you need to check for maximum MR only at the locations that are called as the critical points. So what are these critical points? Critical points are basically points or locations in the bending moment diagram where there is a change in slope. So if you think about this particular MZ diagram here, you actually have a change in slope at point C. Okay? So that is a critical point for MZ. Now, if you look at the bending moment diagram MY, you have a change in slope at point B. So point B is a critical point for MY. Now, what you have to do to find out the maximum MR for the entire shaft is to look at each critical point. So you have to look for critical points of MZ as well as the critical points for MY. And at those locations, you find out what MR is, and you can essentially pick out the maximum MR from among those locations, and that will already give you the maximum MR for the entire shaft. Okay, so let's try doing that. So if you look at this particular segment bending moment diagram here, so if you look at point C, so MR at point C, which is basically a critical point for MZ, that is going to be equal to square root of my at C, the whole square, plus mz at C, the whole square. Okay? Now, at this point C, you have my, which is here, that is going to be equal to 4,000. Okay? And the value of mz at point C is also 4,000. So essentially, you basically have MR at C to be equal to 4,000 square plus 4,000 square. Okay, and the value of that, let me just figure out, that is actually 5657 pound-inches. Okay, now the next critical point that you have to look at is point B. So MR at B is going to be equal to, again, my at B the whole square plus mz at B the whole square. Okay, my at B is this, which is 8,000, and mz at B is going to be at this point, and that is going to be 2,000. Okay, so this is going to be equal to square root of 8,000 square plus 2,000 square, and that value turns out to be 8246 pound-inches. Okay, so essentially we have now evaluated MR at the two critical locations, C and B, and we find out that the maximum MR actually occurs at point B, which is 8,246 pound-inches. Okay, so maximum MR for the entire shaft, okay, occurs at B, and MR max is going to be equal to 8,246 pound-inches. Okay, so this is a much simpler way to find out where the maximum resultant bending moment occurs for the case where all the bending moment diagrams, all the individual bending moment diagrams are linear. Okay, so in many of the problems in this class, we will be encountering problems like this. So this is actually a much simpler way to find out MR max. However, in cases where you have uniformly distributed loads or triangularly distributed loads, in those cases, the bending moment diagrams will not be linear. So in that case, you essentially have to use the general procedure, which is to find out the function for MR for each particular segment and find out what is the maximum. Okay, so now what we have done is we have found out what is the location along the axis of the shaft where the maximum internal bending moment occurs. And in this case, it turns out that it is at this point B that you essentially have the maximum bending moment. And we know that the MR at B is basically equal to 8246 pound-inches. Okay, so now that we have found out what the internal bending moment is, we have to still figure out what is the location on the cross-section of the shaft where you're going to have maximum tensile stress and maximum compressive stress. Okay, for that, it's actually helpful to draw the cross-section at this point B. Okay, so that's what I'm going to do here. So this is the circular cross-section at point B, and I'm going to mark the axis. So this is my y-axis, and this is my z-axis. Okay, what I want you to remember is that we are essentially looking at the shaft from this side. Okay, so that is the cross section that you're looking at. So y is pointing upwards, z is pointing to the left, and your x is actually coming out. That is your direction of x. Okay, so now let me write down the bending moments. We know that the bending moment my at point B is 8,000 pound-inches. Okay, and the bending moment along the z direction is 2,000. Okay, and I want you to remember that these are the bending moments with the correct sign. Okay, we made sure that we had the bending moment diagrams with the right sign in the last lecture, and that is critical here. Okay, so these bending moments are with the right sign. So that is your my and mz, and your mr is going to be along a direction that is closer to my because it is the higher bending moment. So if you define an angle theta here, okay, the direction of mr with respect to z is given by tan theta is equal to my divided by mz, that is equal to 8,000 by 2,000, which basically implies that your theta, the value of theta is 75 75.96 degrees. Okay, so this theta is going to be 75.96 degrees. Okay, so now I'm going to actually erase this x because we have to find out what is the points where you have maximum tensile and compressive stress. Okay, here's something, there's something that important that you need to note. When you have a circular cross section and MR is along a particular direction, the neutral axis, so essentially the line along the cross section where the stress is 0, that aligns perfectly with MR. So your neutral axis here, that is going to be aligned with MR. So NA is neutral axis. Okay. So now you know that from what you learned in solid mechanics, that the points that are farthest away from the neutral axis are going to have the maximum bending stress. So what you do is you draw a perpendicular to the neutral axis, and these 2 points here, let me call them, say, P and Q. Those 2 points are going to have the maximum bending stress. Okay? So in this cross section, again, I want to remember that this cross section is where the maximum bending moment occurs in the entire shaft. And now within this particular cross section, we are looking at which particular points have the maximum stress. Okay? So points P and points Q and point Q, they are going to have the maximum bending stress. Now the question is, which point is going to have a tensile bending stress? Which point is going to have a compressive bending stress? For that, what essentially you use is the right hand rule. So what you do is, you take your right hand and align your thumb, right thumb, along the direction of MR. And now if I do that, what you can see is that if I curl my fingers, I'm going to be pushing into this point P. Okay? I'm going to be pushing into this point P. So push means compressive. So point P is going to be in compression. The opposite point, which is point Q, has to be in tension. That is how you figure out which point is going to be under compression and which point is going to be tension. So again, I repeat it. You put your right thumb in the direction of MR and then curl your fingers. Whichever point you are going to push into, that point is going to be under compression. So in this case, you essentially have P is in compression and Q is in tension. Okay? So now the only thing that is left is to find out what is the actual value of the bending stress at P and Q. They are going to be the same in magnitude but opposite in sign. So sigma, and again the main thing to note is that the stress is in the x direction, which is the direction or the axis of the shaft. That is something that you must always keep in mind. The normal stress due to bending is always along the axis of the shaft. So it's going to be sigma x at P is going to be mr, okay, which is the resultant bending moment at point B, times the radius of the shaft divided by I, which is nothing but the area moment of inertia. So you already know what is the radius of the shaft. You can calculate what is the area moment of inertia. And if you do the calculation, then you find that the maximum bending stress at P is going to be minus 10,499 psi. And the reason that you have a negative sign is because it is compressive stress. Okay. Now sigma x at Q is going to be the exact same value, but with a positive sign. So it's going to be plus 10,499 psi. Okay. That is psi is pounds per square inch. So those are the two locations on the shaft that are going to have the maximum bending stress. One is going to be compressive, one is going to be tensile. Okay. So that basically tells us which points are most likely to fail in this particular shaft. The only thing that is left in the problem is to find out now what is the maximum shear stress in the shaft. And for finding the maximum shear stress, you have to construct what is called a torque diagram. So if you look at this particular problem, you essentially have two pulleys, B and C, and essentially you have unequal forces on the two sides of the pulley. Okay? So what you can do is you can find out what is the external torque that is being applied at this point B, or this pulley B and pulley C, and that is fairly simple. So the external torque at pulley B is going to be nothing but 1000, which is the force on one side, minus 200, which is the force on the other side, times the radius of the pulley. Okay, so the pulley B diameter is 4 inches. So the radius is going to be 2 inches. So you multiply that by 2 inches. And if you do that, that comes out to be 1600 pound inches. Again, torque is like a moment, so essentially it has the same units. Okay, and by virtue of this being in equilibrium, the torque at point C is also going to be 1600 pound inches. Okay, the only difference is that they are going to be in opposite direction so that they can balance out each other. Okay, so now if you draw the free body diagram for torque, okay, so this is point B and that is point C. So at this point B, you have a torque of 1600 pound inches, and the way the torque is going to be denoted is going to be in this direction, because this is the direction of net torque. And if you use your right hand rule, as you curl your fingers this way, your right thumb is pointing to the minus x direction. So that is the direction of TB. Okay, so the direction of TC is going to be opposite, and that is going to be TC. Okay, now what you know is that at any point between A and B, the torque is going to be 0 because there is no external torque between A and B. Similarly, for any point between C and D, the external torque is 0, so the internal torque is also going to be 0. But for any point between B and C, you can find out what the internal torque is, and that is fairly simple. You know that you take a section and then look at the free body. At this point, you have a 1600 pound-inch torque. So this torque here, which we call as TBC, is going to be 1600 pound-inches. Okay, so if you now construct what is called as a torque diagram, this is going to be your T, and that is going to be your X. So the torque diagram is going to be 0. The internal torque is going to be 0 from A to B. From point B to point C, it is going to take a value of 1600, and then again it goes to 0 at point C, and then remains 0 till point D. So this is going to be 1600 pound-inches. So this is point A, B, C, and D. Okay, what you have already found is that the maximum bending moment and the maximum tensile and compressive stress occurs at point B. What you are seeing from the torque diagram is that the maximum internal torque also occurs at point B, which means that the critical point for the shaft is going to occur at point B. Okay, and now once we know what the internal torque, again this T that I am plotting here is the internal torque. Once we know what the internal torque at point B is, it's fairly straightforward to find out what the maximum shear stress is. We know that tau is Tc over J, okay, where C is the radius of the shaft. In this case, I want to remind you that C is 1 inches. Okay, and you know what the torque is at this particular point, that is 1600. You can find out what J is, which is just the polar moment of inertia. And if you calculate what tau is going to be, and that value is going to be equal to 1019 pounds per square inch. So the maximum shear stress is going to occur at every section between B and C. So if you look at any section between B and C here, and you look at the cross section, the maximum shear stress is going to be there. And of course, you know that the maximum shear stress occurs at the circumference. Okay, so it's at the circumference that you have the maximum shear stress. Okay, so if you go back a slide, so this point P and this point Q here, okay, those points are also going to have the maximum shear stress because they lie on the circumference. Okay, so from this construction, we can find out which point is going to have the maximum tensile stress, maximum compressive stress, and the maximum shear stress. Okay, and that essentially is what is required to figure out which point in the shaft is most likely to fail. Okay, Thank you, and I'll see you in the next lecture.